Function as power series part 2. Term-by-term differentiation and integration. The derivative of a polynomial is done by differentiating term by term. For example, in order to differentiate this polynomial, we will differentiate each one of the terms, and when we put everything together, we get the answer. Now we would like to investigate how can we differentiate a convergent power series. Instead of directly do this, I'm going to write the series as sum of terms. Now I can differentiate each one of the terms exactly like I did in the above polynomial. This process is called term-by-term differentiation, and the magic is that this can be done if we have a convergent power series. Let's now see everything written using the sigma notation. We want to differentiate the power series, a convergent series, otherwise this is meaningless. In the first step, we are going to separate the first term from the others. The zero term should be separated from the rest of the sum, because this is the only term that it's not multiplied by x to the power. A sub 0 does not contain any x. Now I'm going to differentiate the first one, which is a sub 0, and then I'm going to differentiate all the other terms. We know that derivative of sum is sum of the derivatives, so I'm using this fact to put the d dx in the summation. And because d dx is related to x to the n, I can write the second term as a sum of n runs from 1 to infinity a sub n d dx of x to the n. Again, because a sub 0 does not contain any x, the derivative with respect to x of the term a sub 0 is 0. Now we are actually differentiating the x to the power of n, and we get that this is n times x to the power of n minus 1. We start here and we end up there. The same is with integration, term-by-term integration of a convergent power series. In order to integrate this power series, we are going again to switch between the sigma notation and the integral sign. Now we are going to perform term-by-term integration. First, I like the integral sign to be near the x to the n dx. And now I'm actually taking the antiderivative of x to the n to get x to the n plus 1 over n plus 1. Don't forget the c, which is the constant of the integration. If a function f can be expressed as an infinite convergent power series, the derivative and the antiderivative of f can be found by term-by-term differentiation and integration. Theorem: term-by-term differentiation and integration. Let fx, written as a power series centered at x equals c with radius of convergence of r which is greater than 0. Then f is differentiable and the derivative of f is the sum an times x minus c to the power of n minus 1 when n runs from 1 to infinity. And the antiderivative of fx is a constant plus the sum of an over n plus 1 times x minus c to the power of n plus 1 when n runs from 0 to infinity. Pay attention, the derivative of x minus c to the n is n times x minus c to the power of n minus 1. And the antiderivative of x minus c to the n is x minus c to the power of n plus 1 over n plus 1. And don't forget the constant of integration, that here it's a not to be mixed with the c, the center of the series. The power series for the integral of fx and the derivative of fx have the same radius of convergence as the power series of fx. The interval of convergence may be different only at the endpoints at c minus r and c plus r. Here is again the function 1 over 1 minus x written as a power series. If we like to differentiate the function, we can instead differentiate the sum. We are going to split the zero term from the first of the terms. The zero term is x to the 0, which is 1. It does not contain x's, so that's why we like to split this from the rest. d dx of 1 is 0, and then we are using the property, the derivative of the sum is the sum of the derivative. So I can switch between the sigma notation and the d dx. Now we actually have to differentiate x to the n, and we get the sum of n times x to the power of n minus 1 when n runs from 1 to infinity. The radius of convergence is 1 because the original function f has radius of convergence which was 1. We will have to check the endpoints. To check x equals 1 is a little bit waste of time. If we look at the function f of x, it's pretty obvious that x equals 1 is not in the domain of fx. But let's say that we don't pay attention, we can still substitute 1 for x, and we are going to get that. By the test for divergence, this is definitely going to be divergent. Okay. And then we are checking at x equals negative 1. We are getting the alternating sum of the sum above. And by the alternating series test, again, the series diverges. We conclude that d dx of 1 over 1 minus x is the sum, when n runs from 1 to infinity, of n times x to the power of n minus 1. But now we are actually evaluating the function that is the derivative of fx. Using the chain rule, and we get that the derivative of fx is 1 over 1 minus x to the power of 2. We conclude then that the expression of the function 1 over 1 minus x to the power of 2 as a power series is the sum n times x to the n minus 1 when n runs from 1 to infinity, and this is true to all x's such that x in absolute value is less than 1. The main idea was we start with one function and we created another expansion as a power series for a new function. Find the power series for the function ln of 1 minus x using the fact that the derivative of the function equals negative 1 over 1 minus x. Note that x equals 1 is not in the domain of the function. Because the derivative of ln of 1 minus x is negative 1 over 1 minus x, in order to find ln of 1 minus x, I have to find the antiderivative of negative 1 over 1 minus x. It's better just to distribute the negative sign and to have the antiderivative of 1 over 1 minus x. We will write 1 over 1 minus x as a power series. We recall that the radius of convergence is 1. We will replace now 1 over 1 minus x with the power series. Now we will perform term-by-term integration, and we will get this because the antiderivative of x to the power of n is x to the power of n plus 1 over n plus 1, and then we have the constant of the integration. A function cannot contain plus c, so we have to find a constant. We are going to substitute 0 for the x. We are substituting 0 into ln of 1 minus x, and we get ln of 1, which is 0. On the other hand, when we substitute 0, we get c minus sum of zeros, which is 0. So we get that 0 equals c. Now we know that the power series expansion of ln of 1 minus x equals negative the sum n runs from 0 to infinity of x to the n plus 1 over n plus 1. Now observe what we called shifting indices. It's customary to express the power series of this function starting with the index 1. This is okay to start with n equals 1, but because I'm starting with 1 instead of 0, I have to reduce one index for each one of the n's in the sum itself. So instead of n plus 1 in the sum, I will have n, but the summation will start with 1 instead of 0. Now we know that we have only to check one of the endpoints, and when we are checking at -1, we will get the alternating harmonic series, which is convergent. And we conclude that ln of 1 minus x equals negative the sum when n runs from 1 to infinity of x to the n over n, and the series converges for all x's that are greater or equal to -1 and they are less than 1. The end.